Welcome to this third video lecture. In the previous two ones, we introduced dynamical systems and differential equations to describe them. In particular, we stated what is called a state space representation that links the system inputs to its states. However, all that discussion was a little too mathematical and all examples we gave were a little too mathematical. Now we will go to physics to extract a few differential equations that describe actual physical and engineering systems. And the most fundamental equation in physics are Newton's laws of motion. But before we can state Newton's three laws of motion, we need to give a few introductory definitions. So this over here is called the frame of reference. It allows us to tell where an object is in space. For example, this point over here has coordinates x and y. If we combine these coordinates in a vector, then this is the position vector. We denote the position by r. We will define now two very important quantities in physics. The first one is the velocity of an object. The velocity of an object is the rate of change of its position, r dot, which is the vector x dot y dot. Second, we will define the acceleration of an object. The acceleration is the second derivative of the position. Equivalently, it is the derivative of the velocity. And now, with that in mind, we can state Newton's three laws of motion. For the first one, we will need some help from this guy, who brings in an inertial frame of reference, which is something new. An inertial frame of reference is a frame of reference in which the following property holds. If you have an object, it will remain where it is, it will have zero velocity. So this object has, in an inertial frame of reference, it has two options. The first one is to remain where it is, to remain at rest with a zero velocity, or to move on a line with a constant velocity. V is the velocity as a vector, and when we say that it has a constant velocity, it means it moves on a line with a velocity of constant magnitude. So, all right. So an object here will not move, or will move at a constant speed, unless acted upon by a force. So if you don't apply a force on this object, it will either stay where it is, or it will keep moving at a constant velocity. So what is an inertial frame of reference? It is one in which this property holds. This property is called Newton's first law of motion. But this doesn't sound like a law, it sounds more like a definition. Well, apparently we can think of Newton's first law of motion as a definition, but it signifies a step change in the way people thought back in the day of Newton, because before that time people used to think that when something moves, there must be a force that is applied to that. Now Newton stated that if you kick a ball in space, it will just keep going. It will have a constant velocity, and if there is nothing to stop it, it will just keep moving. Of course, all this holds in an inertial frame of reference. And then this implies something. This implies that if you apply a force, then the velocity will change. This means that there will be a rate of change of the velocity. What is that? This is now explained by Newton's second law of motion. Newton's second law of motion states that in an inertial frame of reference again, if you have an object of mass m and you apply a force on it, if you apply a force F, then the object will accelerate with an acceleration r double dot, which is it has the same direction as the force, and second is given by this formula. m times acceleration is equal to force. Now this says three things. First of all, that the force and the acceleration are proportional one to the other, and this coefficient of proportionality is the mass of the object. Second, as I mentioned before, they have the same direction. And third, and most important for our purposes, is that this is an ordinary differential equation, which is of second order. Of course, we can introduce new variables if we like and turn it into a state space representation. You can do this as a little exercise. So this is Newton's second law of motion, a very important result in classical mechanics. Let us state Newton's third law of motion very quickly, and then we can have a look at a few examples. Newton's third law states that when you apply a force to an object, this object applies always a force back to you. And that force has the opposite direction, but the same magnitude as the force you apply. It therefore states and implies that forces in nature appear in pairs. Second, it interprets the motion of, it interprets forces as interactions between bodies. And third, it leads to the statement of the principle of conservation of momentum. But we will not go there because this is not about physics. We're just using results from physics to derive differential equations we will subsequently study. Now let us give an example using Newton's second law of motion. Say you have an object here in an inertial frame of reference. This is the positive direction of your frame of reference, and this is at an altitude y with respect to the surface of the Earth over here, and it has a mass m. Then we know that the weight of this object, the weight, which is a force looking towards the center of the Earth, is m times g, where g is the acceleration of gravity. Then we can write down the total force that is applied on the system. We'll write F total equals minus mg. Why minus? It's a minus because it goes against the direction that we have specified here to be the positive direction. So if this were upwards, it would be a positive force. Now it is a negative one. Now then, we know that the total force by Newton's second law of motion is equal to the mass of the object times its acceleration. And if we divide both sides by m, we obtain, and this is the equation of motion of this object. Apparently, the mass doesn't enter this equation, so it turns out that the free fall is independent of the mass of the object. Yes, indeed, all objects will fall exactly the same, their motion will be identical, irrespective of their mass. But this, of course, happens to the extent that we don't have any additional forces other than the weight of the object. So if you have a drag force which opposes the direction of motion, that is to say, if you have some friction with the medium in which the object moves, if you have friction with the air, then this is no longer correct. And this is because now in that case, the total force is the drag force that has the upward direction minus the weight. Now the drag force, there have been proposed several different formulas to compute, to evaluate it. One such is the following. This is usually referred to as Reynolds drag force. And this is a beta, which is a constant parameter. It is a constant coefficient times the square of the velocity of the object. And it has the opposite direction with respect to the velocity, which is downwards in this case. So equivalently, and this now is the new equation of motion, which takes into account the drag force. Now, so far we have mentioned two forces. One is the weight, the other one is the drag force, and we have combined them in a couple of examples in one example to derive equations of motion. Let us mention one more force, and this is the restoring force of a spring. So take an elastic spring. It can be, for example, attached to a wall, and this spring has a natural length. Let's say that we place exactly, not here, but let's say we place exactly here our inertial frame of reference, and this is a convenient choice because at x equals 0 we have the natural length of the spring. So if you don't extend it, if you don't squeeze it, if you don't suppress it, it will have exactly this length. Now, Robert Hooke observed the following. If you extend the spring, then the spring, meaning if it is here at the coordinate x1, which is positive, then the spring will try to restore its initial length by applying a force F spring which goes towards the left. So at positive displacements we have negative forces. Then Hooke also observed that if you suppress the spring, so if the displacement is some x2 which is negative, then the spring will apply a force which will again look towards its natural length. Its natural length is here at x equals 0. It will apply a restoring force F spring, which is positive when the displacement is negative. And then Hooke wrote down the following equation. Which is known as Hooke's law for elastic springs. He has a footnote actually. He said that this is true so long as this x remains relatively small. Now let's solve a little exercise over here. Let's do a little example. Say you have a spring and you have a mass m. The spring has a constant k. By the way, this k is called the stiffness of the spring. I forgot to mention that before. K is a constant and it's called the stiffness. Then say you apply a force F on this object. The total force will be what? It will be our force, which makes the object move to the right, minus the restoring force, minus kx. Again, as before, I have placed the inertial frame of reference over here, so when the spring is at its natural length, it is at position x equals 0. This force will pull it to the right and it will be at some different x, and there will be a restoring force F spring. Now this is the total force. Equivalently, the total force by Newton's second law of motion is equal to m times the acceleration. And we don't need to do anything else. This is the equation of motion of the object. One interesting observation here is that these are the forces on the x-axis, on the horizontal axis. There are forces on the vertical axis. These are the, let me erase here a few things to make it clear. So these are the weight of the object, which is applied by the object on the surface of the table or on this surface wherever it is. Now, by Newton's third law of motion, an action, mg, the weight, induces a reaction, another force, which we call N. Now, the sum of these forces is Fy, is the total force on the y-axis, which is what? It is N minus mg. Positive, negative. Now this must be what? By Newton's first law of motion, this doesn't move neither up or down. Therefore the velocity along the y-axis is 0, the force along the y-axis must be 0. So again, N is caused by is a result of Newton's third law of motion, and the fact that this is 0 is a result of Newton's first law of motion. Great. Let us modify this example a little bit. Say now again we have an elastic spring of constant of stiffness K, and we also have a damper. A damper is a device that behaves in a similar fashion as the drag applies a force which is similar to the drag force we mentioned before. The force of the damper is equal to B times x dot, and it has the opposite direction with respect to x dot. So you will see in some textbooks or other resources, you might find B here. We will denote the force of the damper here like that. We don't need the B, it is clear from the drawing. Again, we apply a force F, we apply an external force F, and there is also the force from the spring, the restoring force. Now these are Kx and Bx dot. Therefore, the total force along the x-axis will be the following. And yes, this is again the equation of motion that describes the motion of this object. Very good. We can now solve a couple of more exercises, but I will solve them just half, and you can do the same as homework. So I will start the exercise, and then you can try to solve the rest of it. So the first goes like that. You have two objects, this one and this one, and these are now connected by a spring and a damper. The spring has stiffness K, the damper has coefficient B. We apply an external force F on this object, and we have placed our inertial frame of reference over here. This will be object number 1, and this will be object number 2. This has mass m1, this has mass m2. This is at position x1, and this is at position x2. To be able to solve this exercise, I must tell you that the natural length of the spring is equal to L. So whenever the distance between the two objects is equal to L, then the force of the spring is equal to 0. So what is the distance? What is the distance between the two objects? It is y. Let's call it, no, let's not call it y. Let's call it simply z, which is equal to x1 minus x2. So if z is equal to L, then there is no restoring force. If z is larger than L, then the spring tries to push the two objects together. On the other hand, if the spring is suppressed, so if this distance is smaller than L, then the restoring force tries to push these objects away from one another. I will use now Newton's second law of motion, but because we have two objects, I have to do it twice. So let's do it for object number 1, and I will leave object number 2 to you. It is very useful in such exercises where you have multiple objects to draw the forces that are applied on each object separately. So on this one, we have the external force, which is to the right. We have the restoring force, F spring, which goes to the left. And we have the force from the damper, which is also to the left. Now, what is F spring? F spring is, recall Hooke's law, K, the stiffness of the spring, times the displacement. But what exactly is the displacement, given the discussion we had about L? So it is K times the displacement, which is Z minus L. Z minus L. And what is Z? Z is x1 minus x2. Very good. Now what is the force of the damper? The force of the damper is B times that distance here. As it changes, this change has a velocity. Sorry, that distance, as it increases and decreases, it defines a velocity, the velocity of that distance, which is z dot. So it is b times x1 dot minus x2 dot. Now then, the total force applied on object number 1 is so the total force is equal to F minus K parenthesis x1 minus x2 minus L, and then minus B x1 dot minus x2 dot, and this is the total force. But the total force by Newton's second law of motion is equal to the mass of that object, m1, times its acceleration, times x1 second derivative. So the equation of motion that corresponds to this part of the overall system is the following. I will write it up there. It is, as a result of this equation, and I will leave to you to figure out what are the forces acting on this object over here, and to write the corresponding equation by using Newton's second law of motion. And after you do that, you can try to write down the system equations, the differential equation, in the form of a state space representation. There is one more exercise we can try to solve. Again, I will solve half of it and you can do the rest. We have an inclined plane over here. We have an object of mass m, and I'm telling you that this angle over here is some angle theta, which doesn't change in time. Then suppose that the only force acting on the object is its weight, m times g. And now, in order to make our lives easier, we will turn the inertial frame of reference like that. It will be like that. However, this force is not perpendicular to any of these two axes, this axis and this one. Therefore, we have to decompose it in a way. So mg breaks down into mg along x and mg along y. Now mg along x is what? Let's have a look. This angle is theta. This triangle is a right-angled triangle. So this is pi half minus theta. Therefore, this one is also theta. One way to look at it, at least. And this touches, this mgy touches the angle, okay, in this triangle. Therefore, mgy is equal to mg cosine of theta. Whereas mgx is mg times sine of theta. So along this axis, you have what? You'll figure it out. So I'm going to tell you only this much about this exercise. And the question is, what is the equation of motion? What is the equation that governs the motion of this object? And then after we do that, it will not be difficult to solve also this exercise, to add a few more elements. So in this exercise instead, we have that this angle is equal to phi. This spring has a stiffness K1, this spring has stiffness K2, this damper has coefficient B1, and this one B2, and this is a right angle triangle here. Another question is again, what is the equation of motion? What is the differential equation that describes the motion of this object over here? And what is the state space representation that corresponds to that equation of motion? And with that, thank you very much for watching. Until next time, goodbye.